Okay.
And we're live.
Okay. So welcome to Bite of Physics number 72. You're on Clubhouse, newly on YouTube at the Scientific Discourse channel. Thanks to my buddy Shamash, who also does the Philosophy Wednesday things here on Clubhouse. And we don't have Sam here today doing the chemistry, who does the chemistry shows. We have Ben, who often does Bite of Physics when I can't, does his own takes on things. Go ahead, Ben.
Yeah, I'm thinking of starting regular rooms again, possibly before this. And I might do sci-fi, like hard sci-fi. So because my son keeps talking to me about things like Dyson spheres and the latest idea with the stellar engine. He's like, why would we take ourselves to another star when we could just like use the energy and the mass of the star to move the star with some ridiculous machine and just take our star to another system and then do the short ride when we're near enough the other system. So doing like hard sci-fi on that stuff might be fun. If people are interested, just shout out in the chat or something, and I'll consider doing, prepared slide hard sci-fi stuff. The Martian sort of Hail Mary type shit. Take a topic, dissect it, consider crazy, outlandish ideas, and see where we go.
That's kind of what we're doing today. So what we're doing
Interesting.
today is we're talking about the topic. The title of the topic today is stuff attracting stuff, and it was motivated largely by just thinking about. Well, I don't know what was it motivated. I don't know what it was motivated by, but it's motivated by my kind of constant interest in having people really try to take themselves back, try to forget, and that's what we're going to do. We're try to forget everything you've been told, everything that you think you know. Some people know these things better than others in the sense that they really know them. Most people have just kind of been told these things, have internalized them. They make sense. They're true, but but most people kind of think they're self-evidently true. And the fact is that the stuff attracting stuff thing is a very new idea on the stage of human thought. It only occurred to people about 300 years ago that stuff might attract stuff. But that might be an important fact. I guess I shouldn't say that stuff attracts. It's been for a long time. People have known about magnetism, right? A very weird force. We'll return to that at some point. But the idea that stuff attracts stuff is a very new idea, and it's so internalized. I'm going to try really hard not to use a word that's often used in talking about stuff attracting stuff today. We're just going to talk about it in that way, partly to try to get rid of all of the preconceived notions we have about things. If you open up the slides at the top of the page there, you'll see, as always, this is Biophysics number 72. There's the title. There'll be a link to this discussion eventually on these slides, which will always be available at the link to all of the Bites of Physics that's there at the top. There's a few other links to things on my public pages, Nibbles of Physics, and then really to all of my public documents, including those things. If you have no life and you want to waste a lot of time looking at little treatises that I've prepared on this and that, figures that I've done, and so on, they're all kind of collected there. So let's move. Yeah, go ahead.
May I just say it's completely not a waste of time, because these slides are such good material if you're teaching. You can go and fish for very good ideas there. And I am guilty of doing that myself.
That's great. Thanks, Shamash. And your $20 is in the mail. So never fear.
Dude, $20? Wow,
Oh.
I should do this more often.
All right, so slide 2, preparing for today's thought experiment. As I said already, forget everything you know, indeed everything you even think you know about physics, other than one, and this is kind of important, that the universe is apparently filled with stuff, and two, that the fundamental idea of physics, I shouldn't say that. Yeah, don't forget that the fundamental idea of physics is that what stuff does is determined by rules. There's fixed laws. We may not know what those laws are, but there are rules that stuff obeys laws. Now, I'm saying forget all that, but in fact, really at the beginning, all but that. But at the beginning, I want you really even to kind of forget that. We're definitely going to move to that. I don't want you to think that I'm abandoning the ideas of physics and the idea of a universe filled with stuff that's all that behaves according to those laws and all that. But that's all that stuff is pretty new idea, and we'll see how that works. Those things didn't occur to us until pretty recently. And so just to start off, I'm going to say, just suppose, including those ideas above, that all that stuff is distributed like as in that picture there, which is to kind of indicate that there's more stuff in some places and less stuff in other places. And then the first question is, what could happen next? I mean, what might happen as time goes on, whatever time is, right? We won't worry about that today. And after that, not just what could happen next, but then once we've kind of decided what could happen next, it's worth looking at what does happen next and see if how many of the things we thought could happen are kind of borne out, and then to kind of settle on why we thought those could happen as candidates for why the stuff happens the way it does. That may sound all kind of nebulous. That's a good word for that picture. But so if you go to slide 3 then, along the lines of what could happen next, we're going to think about things like what kinds of rules could you imagine might operate? What kinds of rules could determine what could happen next? And if could those rules distinguish between different kinds of stuff? You might think that those rules would be based on an interaction, but that's probably something, kind of a bias left over from stuff that you think you know that you haven't forgotten adequately for the purposes of this presentation. But we're going to return to interactions, the idea that stuff might interact with stuff. But properties of stuff that might matter. The color of the stuff, maybe that matters for what happens next. Its volume, how hard it is, how fast it's going, where it is, how near it is to other stuff, the direction maybe to other stuff, properties of the other stuff. Some of these things you'll say, oh, I know what he's talking about, but I'm trying not to just say, I'm just trying to kind of think about all of the things that might matter, properties of the matter, properties of space, etc. too. So I say, what kinds of considerations might you expect to limit the possibilities? Will you expect that whatever happens next will happen because of isotropy? These are kind of advanced ideas, but the idea that there's no special directions in space. A crystal is kind of a funny thing because a crystal has some very special directions. Can you have crystals in a space that's isotropic, that has no special directions? How do you get a crystal if space itself is isotropic? Homogeneity, if there's no special places. If there's no special places, can you have big things here and small things there if there are no special places? These are just, I'm kind of just spitballing all sorts of weird things to try to get you to contribute others. So what do you think? And notice that there's one kind of important thing in the properties list that I kind of purposefully left out, partially because it's a little hard. I can kind of define color. I can kind of, at least for me, I can tell you what a green thing is. I can tell you what a red thing is. I can define volume pretty easily. I can measure it with meter sticks, etc. Hardness, velocity, position, those are all kinds of easy things to define, but there's at least one property I didn't mention, which you might think about. Anyway, I just want to leave it there and just ask, what kinds of things do you think might matter? If you really try to empty your brain and just imagine, are there any properties of matter or properties of space itself that you think might matter?
Mass?
That's the one I left out. Yeah, indeed. And I left it out largely because, at least at this point, it's not very easy to define it without talking about weight, and then weight leads pretty quickly to to a word I don't want to say in this bite of physics. It doesn't have to, but that is, yeah, it is one I left out, and I invite you or anybody else to talk more about it from a naive standpoint, or
Oh,
anything else if anybody has.
gravity,
Oh, no.
stay away from me.
Okay, you can say that word if you like, but I'm not saying that word. Go ahead,
Well,
Benjamin.
mass can be evaluated in the vacuum of space as the resistance to a change in direction.
Okay, that's right. I'm already made nervous by your using words that imply that you're a modern person, but you're not wrong. And of course, the idea of mass certainly would be known to ancient people, whether they thought of it in terms of the weight of an object or just how hard it is to move that object. So it's certainly not off the table. In fact, it really should be on the table. I kind of used volume as a stand-in, but of course, big things can be kind of hard to move or easy to move, depending on some other property that they might have.
Yeah, but the mass can be evaluated in any context by rotation.
Well, once again, I want to really stay away, though. I mean, I think that your comments here are not comments you would have made if you were living on the earth 5,000 years ago. So I'm trying to kind of stick to a
But who
5,000
did the
year old
work with the
state of
rotating
mind.
water in a bucket? I thought that was understood pretty early, that water slipping up the sides of a bucket.
I think it was
Uh,
certainly understood early as to why it happens, or as to whether there's anything to wonder about might be another question. Um, people might have wondered about it, but I don't think my guess would be that a Stone Age person would have said, "Man, when I spin around, I get dizzy." Oh, it's because I'm spinning around. Okay, yeah, right. Spinning around is different from not spinning around. Spinning around makes water climb up the sides of a bucket. Um, I, I'm not sure it would have
so the
occurred
Greek
to them to say
Olympics,
anything
the
else. Go
Greek
ahead.
Olympics had a long jump, and in the long jump, uh, the jumpers would start with these weights, and they
Ah,
would run with the weights, they would jump with the weights, and in the air,
throw them out in
they
front.
would throw the weights, no, not out in front,
Out and back. Yeah, I see, of course. Yeah.
and behind, right? They would throw the weights
Right.
behind themselves as a
Right.
way of extending their leap.
Right.
And
That's right.
for all of that to make sense, I think you have to have a sense, not
You
of
have a
weight, but
sense.
of
That's right.
mass.
And I think it's a really good point. I mean, the point is that we have an intuition for how things work, whether or not we have a theory that explains them. Our intuitions about the way lots of things work are really good. For instance, we know intuitively Newton's third law. Every time we get up and walk across the room, we know that in order for us to go forward, we have to push backward. And that's a weird thing when you kind of put it that way, but nobody ever did. Stone Age people wouldn't have even put it that way. They'd say, "Oh, I get up and I walk across the room." They know intuitively that to do that. Of course, they didn't have rooms, but they know intuitively they have to push backward, but they probably wouldn't have marveled at it or even thought, certainly wouldn't have thought about anything like Newton's third law. In some way, Newton's third law is kind of weird, right? It's just a statement of something that we all know intuitively, but it turns out to be really important because once you actually put it on kind of mathematical terms, then you can do surprisingly more complicated things with it. So yeah, no, I think that's all. Those are all really good examples. But I would just invite everybody to realize that our intuitions for how things work are often pretty good, even if we have no idea really why, or don't even think that we need an idea, and don't even really understand what it would mean to ask, well, why does that happen? What do you mean, why does that happen? It happens. That's enough for a Stone Age human being.
And a quantum physicist, if you
Yeah,
can.
okay. I knew we'd have to get there. Go ahead, Shamash.
Can I be the Stone Age person?
Yeah,
Or
please. I need
can
Stone Age people. I need to
yeah,
surround
I'll
myself.
be the perfect Stone Age person. So I don't know about any attraction you're talking about. This is weird business,
Right.
right? Like all I have is a couple of stones and some sticks, and that's all we're using. If you're talking about attraction to my females comrades over there, yeah, that I understand, but that's it.
Hmm. Yeah, that's spoken like a true Neanderthal, Shamash. Let me congratulate you
Ooga
on
ooga.
that. That's right. Scargo cloak, I think is the way I usually express that. By the way, I just went through my slides and put numbers on the pages. If you had gotten far enough to notice that every page was numbered 2, you may refresh now and they won't be.
Oh, good. You
Okay.
told me because I have a downloaded version. 1 second.
Okay, good. Yeah. It's always probably good to download it after the fact because it sometimes does change during the presentation.
The problem is I cannot use the Google Chrome to stay with your point of view because the resolution is very bad because I'm streaming.
Uh, oh, yeah, and all sorts of considerations. See, these are things I don't even have to think about because I'm
Yeah,
basically
but
in the
I'm a
Stone
caveman
Age.
now. Shh, we don't
Yeah,
know about
well,
all,
you're
all of
not the
that.
caveman. Yeah, no, good. So that was very good, and I think that was an important kind of attitude that I want everybody to bring here. So with that in mind, let's go on to slide 4 and just ask things. So what would the evolution of that universe that I proposed at the beginning look like if, quote, nothing happens? And maybe to start that, I would say, well, what would nothing happening look like? So somebody give me their idea of what it would look like in the future if, quote, nothing happens. And then maybe in the same breath, tell me what you mean by nothing happening. David? Oh, sorry. David's unmuted. I don't know if that was because you wanted to say something or was unmuted. Yeah, no, I think, David, you're still unmuted, but maybe you didn't want to say something.
I thought I was muted,
Oh,
but I could talk about nothingness. I can speculate. Um, it's no interactions because there's no particles to interact.
okay. I think the word interaction is kind of a weird thing at this point. We certainly, if in a caveman kind of way, I think the only thing that would mean an interaction would be coming into contact with something, except for this weird thing that Claudius over there found this magnetite that exerts these influences at a distance on something else. But primarily, the idea of force for a caveman is kind of, you touch something and you shove it around and all that. I mean, you don't really, not even really thinking so much of forces as you are, contacting something and moving it from here to there. And then maybe at some point you realize that you can let go of that thing and you've made it move in a persistent way, at least a semi-persistent way. So there's some things to explain down the line. But I think the word interaction is a little weird at this point. We are going to use it pretty soon here. But if nothing happens, so first of all, what do I mean nothing happens? If nothing happens, one way of thinking of that is when nothing's moving, right? If things are moving, then something is happening.
Yeah,
Uh,
definitely. So if you ask me as the resident caveman, what's alive and what's dead, I'll tell you things that move on their own are alive. And so, I'll just look around and see, people falling asleep, and I'll think they died, but then they will wake up later, and it's like, oh yeah, we fall asleep. They feel unconscious, or they move in their sleep on their own. So yeah, they're still breathing. Their chest is moving. That's fine. But when all of that stops, yeah, then we start becoming worried. Then of course I'm not worried about the rocks moving because they're not alive. They just don't move.
Yeah, that's great. Man, this is when you really like having a philosopher in the house because they're able to, get rid of all of those preconceived notions and get down to the essence of things. That was
Bring
really
it
good,
on, baby.
Shamash. No, that was great because I think really if nothing happens, then one definition of nothing could be, well, nothing is moving. If anything's moving, then something happens. So if nothing happens, then it's just going to continue looking exactly like it did in that first picture. Now, a modern mind might say, well, nothing happens means that whatever things are doing right now is just going to keep doing it. That's a kind of a modern idea, right? That's a Newton's first law idea, objects in motion, staying in motion, and all that. Not something that, certainly not something that cave people thought. Cave people certainly didn't think that an object in motion stays in motion. If you don't do something to keep it moving, it's going to stop, right? I mean, that's what things do. So if nothing happens, maybe things are moving right now, but if nothing happens, then certainly, I think, everything's going to stop and you're just going to end up with a bunch of stuff in some configuration. It might not be the configuration it started with, but it'll, whatever configuration it comes to, maybe it'll stay there. I don't know. What do you think? Well, we don't have to belabor the point. What if the rule is that stuff speeds up? Then what would the universe look like? I guess it wouldn't look
Stuff
very
speeds
different.
up on their own.
Yeah, stuff just, yeah, I mean, it's just really spitballing
Yeah, I've
here.
never seen that. But we've never seen that before. Like, I struggle with my mates, to throw the javelin long enough. We have a dude who can throw like 10 paces to attack the gazelle, and he's the thrower in the group. That's all he could do, right? But most of us can't do it, and even if we can, it'll not reach with enough. How to say this now? Cavemen don't know this. Impact, I want to say kinetic energy, but they don't know that. They will not do the hooga thingy that kills the gazelle if you throw it long enough. You have to be close.
Yeah.
So things don't get faster on their own like that. There's no way.
That's right. It certainly is the case. We can still speculate about what would happen if that were a rule. If stuff sped up, then I guess you'd end up with stuff moving faster for one thing. But as far as what it would look like in a picture, I don't know. What would it look the same? Does that depend on
It
if
sounds
the
like an
universe is?
unstable. Things would
Yeah.
accelerate into away from each other or colliding into each other.
So does that mean? And so, for instance, if the rule was stuff speeds up, would everything be kind of further away from things in the end? What do you think about that? Let's just ask that. Would stuff end up being further away from other stuff if the rule were stuff speeds up?
My intuition, just in my head, I think of an explosion and everything accelerating away, but that has actually some kind of starting energy.
Exactly.
But
And a center point, right?
yeah, and basically it's centrally from every point, everything's getting farther away at every successive moment, even faster.
Right.
I do understand acceleration. I kind of went from the YouTube back to here. Are we supposed to be taking like tabula rasa, like we don't know things, or?
Exactly. Yeah,
Okay.
really trying to be tabula rasa as much as possible. And I think the stuff speeds up thing is kind of interesting because I think you can make an argument that things will look different in the future, and you can make an argument that things will look in a picture, at least. If I were to take a picture of this universe later, it could look either different, qualitatively different. Like, for instance, less stuff around in any given volume. There'd be less stuff. And I think you could also make an argument that that wouldn't change at all. You'd have the same amount of stuff in every volume. Can you see how you could have either one? Somebody tell me how you could have either one, or tell me how you could have one of those, if you think one of those would be.
It's about the direction of are things moving towards each other or away?
Well, so what would that mean? I mean, I don't know what it would mean for
You could
things
accelerate
to move
toward,
toward
like,
each.
you could.
So okay, so you're
If it's
thinking, but I
coming
think
faster, you
you're.
could be attracted like a magnet.
See, I think you haven't quite erased your mind yet, right? The rule here is merely stuff speeds up. There's no interactions, there's no attraction. The rule is just stuff speeds up.
So you're asking if the rule that we discovered was the stuff speeds up, then what the consequences would be?
Yeah, it was certainly there's one consequence is everything would be moving faster, right? That's one
and this is
consequence.
exactly what we don't use. I don't know where you got that idea that stuffs move faster. Like, I wish it did, but it didn't.
Something can roll down a hill faster and faster away from you. It's vantage points, so they're relative.
See, well, I'm thinking about on a kind of a universe thing. Suppose the universe is infinite, um, and everything. First of all, suppose the universe is finite, whatever that means, and stuff speeds up. Then would a picture
Then we
later
will hit the
on?
boundary, no? It's
Then I
like
guess
when
it
we
would
have
hit
it's
the
like when we have the
boundary.
sheep. It's like when we have the sheep and they want to jump, so they will hit the fence because they're just moving faster. And just imagining like a sheep that is very very upset, and it's just hitting the fence from one side to the other.
Yeah, bouncing back in, right? So certainly, like a gas in a box, um, doesn't speed up, but on the other hand, it's kind of kept there by something, and therefore, no matter even if you did speed it up, even if you heated it, pictures would look the same, right? The gas molecules would be the same distance apart, even if they were all moving faster. So a picture might look the same, even though things are moving faster. That would be a universe in which stuff speeds up. A closed gas in a container that's being heated is a universe in which the rule is stuff speeds up. And yet a picture of that universe is going to look the same at any later time because all the same molecules are in the same volume and all that. Okay, well, I don't really want to belabor this point. I'm just really trying to get everybody in a properly stupid state of mind, right? We don't know anything. We're just kind of spitballing about what could happen. What if stuff slows down? Well, we already kind of talked about that. That's one version of nothing happening. If nothing happens, then stuff that's moving is going to stop because that's kind of what you think nothing happening mean. Nothing happens means nothing to keep it moving in that case, I guess, right? What if like colors repel? And what would that mean? How like would they have to be? Um, and what if they repel, but they don't interact at all with other colors? Then I guess maybe you just have a version of stuff speeding up. Um, what happens if they attract other colors? What if like colors attract other colors? I suppose you could say, well, that sounds like something where ultimately you're going to have all colors together, and then maybe that makes white, or at least whatever you think a combination of all colors is. Why colors should have anything to do with repulsion and attractions and other thing. But once again, I'm really just trying to. All of this stuff is just attempts to um, to just spitball, not knowing anything. We do bring our preconceptions, as Benjamin was saying. We do know some stuff about what does happen. So some of this stuff just sounds ridiculous. What if the rule is that stuff repels other stuff? Then, presumably everything is going to try to get further and further away from everything else. Does that lead to a situation if stuff repels other stuff in a finite universe? Then presumably you end up with a steady state, maybe not, where everything is kind of evenly spaced as far away as possible from everything else. You know, um,
Funny
what if
that
it?
you mentioned that. We were around the campfire the other day after he was cooking dinner, and the fire was red, and then there was these red things coming out of the fire, and the fire was shooting them out as if it was burping, right? As it ate the wood, it was burping these red things out, and I was asking my mates like, why did this happen? And then the conclusion we got is like these red things, because they are like the fire, they don't like to be together because they will eat each other. So the small things will just get away.
Well, there you go. That's spoken like a true caveman, Shamash. Good, congratulations. I assume these are just little flaming embers that are being carried by the
Oh, I don't know what they
fire.
are.
Yeah, I don't know if you're actually trying to be a caveman now or not. But
Oh, I
anyway,
am
I like
actually a caveman.
it. All right. Well, maybe we've spent enough time on this. There's lots of things here, but I did want to say, what if stuff attracts other stuff? Because that is kind of it's pretty easy to imagine. If stuff attracts other stuff, then presumably it gets clumpier. You get bigger things over time, and maybe eventually you just get one big spherical thing? Would it be spherical? If stuff attracts other stuff, then the way the stuff can get closest to each other is by being spherical. And if everything ends up in the same clump, then presumably you just have one big spherical thing. And that certainly sounds like, I mean, I don't know if you can think of any other endpoint for a rule with stuff attracting other stuff. We do have that rule, and nobody thinks that's the end point, so that's pretty interesting. Anyway, any other comments on this before we go on? Okay.
It's very weird that we learn about gravity and nobody thinks that things will all end up in a big ball until they hear about the Big Bang, and Hubble is like, yeah, of course, right? Like, of course it has to be the case.
Right, and I think that's really a good thing. I mean, there's a really good example of how hard it is for us to put things we know out of our minds, because Einstein was acutely aware of the fact that a universe filled with stuff that attracts other stuff is going to end up in a big spherical ball unless you insert some magic into your theory to keep it from doing that. And that's what he did. He inserted magic in the field equations so that the universe wouldn't turn out to be one big spherical black hole. That's kind of an interesting little historical point as well, called the cosmological constant. Yeah, so that's how we don't worry about that these days. We don't think about it because we say, well, it's not going to do that because stuff is expanding away from everything else. Yeah, but we've only known that for 100 years, and the only reason you know that is because somebody told you. So that's really important to keep in mind too. So let's start then. Let's start the journey from caveman philosopher to modern times, just by asking, what is it that we casually see? And I put casually in quotes because cavemen were casual about their observations in a sense. They didn't have instruments. They didn't make precise measurements, but they were not idiots. They looked at the sky. They looked at the earth way more than we do. And they had some pretty clear understandings of what happens, what is out there. And so, I mean, for instance, one obvious thing, the most obvious thing, is there's a really big, bright, I shouldn't say really big, there's a big, bright, circular thing that's always the same size in the day when it's visible. It's always the same size. It's daytime when it's visible, and it is nighttime when it's not. There's a little transition in between, but that's kind of the most obvious thing about the world that we live in. There's one other big, much less bright, circular thing. It's always the same size as the other thing, and it's visible day and night. And it has these weird phases, things we call phases today. It does this weird phase thing. It would not have escaped their attention that the bright part of that thing, when there's only part of it that's bright, always faces the direction. If you draw a line kind of in the sky, that line goes toward the sun. Sometimes there is a sense in which it appears not to, but it would not have escaped their attention that generally the bright side of that thing is facing the big bright circular thing that's always the same size in the day, and maybe at night, that it's even if because they knew where it was at night. They knew what happens. They knew that it went down on the other side when it wasn't visible, but didn't mean it didn't exist, presumably. But they didn't know that, of course. They didn't know that for sure, but it made sense. There were lots of other points of light in the sky that are only visible at night. But and this is kind of an important point. It's something that a lot of people miss. Presumably, all those points of light are there in the sky even during the day. One of the clearest indications of that is that after the sun sets, there are almost immediately stars that become apparent very close to where the sun is, right? Those stars were clearly in the sky because everything in the sky, one other thing they notice is that everything in the sky is going around them once a day. with minor exceptions. There are a few things that take more or less than a day, but not much more or less than a day. Nothing changes its size. Nothing changes its orientation with respect to other things, except for these few things that slowly move relative to all those lights. And those lights are clearly there, as indicated not only by the fact that they're right there near the sun right after sunset, but most importantly, perhaps in astrology. They knew that the sun was in Aquarius, even though they couldn't see Aquarius. They knew because they knew where the rest of the sky was. They knew where the sun was. They knew that it was in Aquarius, specifically when they didn't see Aquarius. So that's kind of I mean, it's really a testament to the fact that they watched the sky very carefully. They knew stuff like that. There's no way we know stuff like that now, except for the fact that other people tell us that stuff. I just think that's kind of an interesting thing to understand fully as well. So I already said almost all lights in the sky rigidly maintain their positions with respect to each other. Their constellations, they're the same, from any place you go, you see the same things. Everything in the sky essentially makes one complete circuit overhead, east to west, at a constant rate, presumably back underneath us to the starting point each day. Ancient cosmologies either said that explicitly or were kind of mum on the point. But clearly things weren't in the sky. When something was in the sky, you could see it unless it was something that was being drowned out by the light of the sun. And that weird blueness during the day, there's something that would have been very weird to the ancients, is the fact that the sky itself is light during the day. Lots of ideas, I'm sure, about why that would happen. It's also perfectly clear that the ground is flat and that displaced or thrown stuff falls to the ground. Does any of that suggest simple universal rules? And does any of it suggest that stuff attracts stuff? Now, I might say that there might be some universal rules that are suggested, at least for the stuff up there in the sky, and maybe for the stuff on the ground. But there's nothing that suggests the stuff in the sky is the same stuff as the stuff on the ground. And there's really nothing that suggests that stuff attracts stuff. There's nothing in what they see those things in the sky doing that suggests to the casual observer that things are attracting other things. There is this, it's obvious that the ground is a different thing. It's flat. Everything goes around it. And that's what you see. And so what do we make of our casual observations? Go to slide 6. Let me just stop for a second if anybody has anything to say on slide 5.
I would. Sorry.
Let Shamash go first here, Benjamin, and then we'll get to you.
Very quickly. About stuff falling down. I think that would be a rule. I from reading mythology and all texts and religions, etc. We have descriptions even through the Middle Ages, very shyly, but before then, of course, that people believed that the stuff in the sky as well is subject to that rule. And it is apparent because they would see sometimes, occasionally, what they would call shooting stars or falling stars. So the stuff above is held by a supernatural force. And sometimes things from above fall down, like rain, like hail, snow, or even one of the stars. And there are many religious stories about why those stars fall. One of them is the devil has escaped hell, and he's kind of listening to what's happening in heaven. And God shoots the devil with one of those stars so that he sends him back down to hell. So we know that stuff fall down. That's it. That's all we know so far.
Right. No, I think that's really good. And especially what you said. I mean, clearly, for the most part, there's some supernatural weird thing that keeps most of the stuff in the sky from falling. But equally clearly, anything that comes close to the ground falls to the ground. Right. That's equally clear. Rain, meteorites, snow, people, rocks thrown in the air, etc. Go ahead, Benjamin.
So I think people would have been acutely aware of the fact that they themselves can fall down,
Mm-hmm.
and that small distances are manageable and larger distances have more energy and become more dangerous.
Mm-hmm.
And
Yeah,
they would have developed a sense of that relationship.
that's
I
a,
don't know
let me just
why, but I
stop you
have a
there for a
fear
moment.
that's natural.
Yeah, let me just explore that for a moment because I think that's really an important thing too. People clearly knew that falling from a small height was less dangerous than falling from a big height. Um, Whether they would have understood that in terms of just the velocity, whether they probably would have kind of innately understood that that's because you end up hitting the ground faster if you fall from a big height. But exactly what that means, why that happens, um, that's kind of another thing. Things do apparently speed up when they fall, but how they speed up. Um, what one thing they were pretty clear on is that heavy things hit the ground much harder than light things, and they weren't able to very carefully distinguish between, very carefully understand what that meant. That was not about in general moving so much faster. So there's a real difficulty separating out the effects of the size, or dare I use the
So
word
I
mass, of
wonder,
the object and the velocity.
the second thing I wonder if they put together was that some rocks indeed stick together,
Mm-hmm.
and they have
You
this
mean magnets?
characteristic. Yeah,
Right. So magnets, and I
and
think that's a really, let me just stop you there too, because I do think that's a really important observation, and it's important to understand how weird that was. Magnetism was an incredibly weird thing because they had no experience. They didn't think they had any experience with stuff actually like moving other stuff, right? I mean, that's certainly not what's happening with the
yeah,
Earth.
but the thing about a magnet is that with a magnet you can make something fall up.
Yeah,
And if they
right.
had gotten to this notion of making something fall up because of a magnet, then they would have started to at least be able to express that there's something about a magnetic force on a small scale that is similar to what a human does when they jump off of
See, I don't think
a cliff.
I actually you may be right, but I don't see any necessity of that for reasons that we'll get to here in a minute. I don't think there's any reason to think you still haven't evacuated your mind well enough. Let me just jump to it. The point is that there's no need for let's see. Do I want to say that? Yeah, well, let's go through slide 6 because I think we get to it here. So what do we make of this? The observations make it really clear that all these things move around in a kind of a celestial sphere. The celestial sphere was very clear to the earliest people who made just uninstrumented observations, making casual observations. There was a star up there in the north because most of these people were in the northern hemisphere. Let's at least confine ourselves to that for the moment, even though it's not quite true. Um, there's a star up there that never changes its position. All the other stars do execute circles around it, some of which you can see them all the time. Every night you see them because they're close enough to that star that things circle around. Others you see only at certain seasons, having to do with whether the sun is near them at that part. The sun travels along a path around this celestial sphere that ancient people knew about the ecliptic. They knew that path was inclined to the kind of point to the circle 90 degrees away from. They wouldn't have said 90 degrees, but they knew there was a kind of a circle 90 degrees away from these stars that we will call the equatorial plane, but which is just a point that's 90 degrees away from the pole star, and that the sun travels around a path that's similar to the equatorial circle, but is inclined to it by 23 degrees. They would have known that angle, although they wouldn't have expressed it that way. So they knew all that stuff. But the Earth, I think, certainly, I don't think, it's not just that I think, it's clear, it was entirely different from the lights in the sky. There was something supernatural going on in the sky, meaning different from on the Earth. The Earth is made of stuff that obviously wants to be and therefore moves to be as close as possible to the center of that sphere, right? There's the universe. You're looking out at the universe. We are at the center of that universe. And what could be more natural than for stuff to want to be at the center of the universe? And that's all you needed. You didn't need any magnetic like attractive force. You just have stuff whose nature is to want to be at the center of the universe. So what do we think about all that? And as I say, and you notice I say at the bottom there of chapter 6, notwithstanding very weird magnetic effects. So there's something very weird about magnetism. And at some point people understood there was this other kind of electrostatic thing. They had some experience, but the most early experience with things influencing other things, really influencing other things at a distance, was magnetism, and that was a very unique and weird thing. What do we think?
But the key is that magnetism is a strange characteristic of some objects to ignore gravity or to ignore the general rule of falling. It was an exception. It was a violation of the rule of falling. It wasn't a violation of the rule of how hot things burn you or some other rule. That heavy things hurt when they hit you. It didn't violate that rule, but it did violate the rule that heavy things tend to fall down, which is why I think...
See, I guess I disagree with you there, because I don't think there was anything, they didn't see anything in magnetism that violated the rule that stuff wants to get as close to the center of the universe as possible.
I agree with that, John. I was going to say,
Yeah,
it's more general than that. It's just that these two things attract each other or repel each other. It's kind of as simple as that, I think.
Right. You can move stuff around with magnetism, but it doesn't violate the rule that stuff wants to get close to the center of the universe.
But if you want something and I want something, then we have a tug of war, and one of us gets to have the thing, and the other one of us doesn't get to have the thing.
If you want a general
rule,
rule,
if I hold a magnet, right, is that the hanging magnet is attracted to the other magnet, and the Earth, which would usually attract a rock that's in space, it loses. It doesn't.
No, I don't see. I don't know. I think that's overly. Go ahead, Ben. I think you're saying.
I was just going to say, I like the approach of saying which of their general rules does it challenge, but I think more the general rule it challenges is that two things need to touch each other in order to move or affect each other. I think that's the thing that it challenges. It's suddenly, wow, action at a distance, and I think that's what every kid that first uses a magnet. That's the intuition you have challenged there. Every other time you've interacted with the world, you've had to make physical touch, and then suddenly these things as a gap. That's cool. Spooky action at a distance, if you like.
Yeah, that's right. And it doesn't change, right? You can push something. You can, if you're very careful, you might be able to push something upward, but ultimately it's gonna it's an unstable thing, and it's gonna find its way to the Earth. Stuff still wants to be at the center of the universe.
We must not forget that these magnets were naturally found for the most part of history, and they were weak because they were naturally found, and they were usually found already attached to other particles like ferrometals and stuff, and making them interact in the way we see neodymium magnets interact today is just not available. These were just weird rocks. And the only explanation is that they're magic, because you could not make that they only attract ferrometals. Just not it's not accessible to you until you discover most of the elements on that periodic table and their properties, and you do a lot of experiment. It's just not accessible, because why do you feel that force when you have the magnet attract to the sword or to the stick that you have, the metallic rod, but not attract to the table or to the door or to your hand itself? So the most obvious explanation for them, I would say, is that it's a magic rock. That's it.
Yeah. Yeah. No, I think that's probably right. But let's leave magnetism behind. Let's concentrate on the obviousness of the flatness and the way in which that encouraged people not to wonder at all about why stuff falls. It's really, I mean, everything that you see makes it clear that the Earth is a unique thing and that it is at the center of the universe. And what could be more natural than stuff wanting to be at the center of the universe? And yet, because ancient cosmologists, Stone Age cosmologists, weren't fools and understood that night happens when the sun goes around behind. About half of the ancient cosmologies are explicit about that in one way or another, and others are less. It's less clear, but certainly don't somehow keep things in the sky. It's very obvious that there's a full sphere's worth of stuff in the sky, and there's only room for half of that sphere at any given time in the visible sky. So the other half of that stuff has to go somewhere else. That's perfectly clear from the fixed relationships of the constellations, etc., and the fact that there's just not room for all of them in half of the sky. So if you go on to slide 7, so the first thing to go was flatness because of two reasons. Probably the most important reason was, by the time of the ancient Greeks, people were traveling in places and keeping at least accurate enough records to kind of come to the dawning realization that it was night in some places at the same time that it was day where they were. And that was a completely untenable thing on any flat earth. There's no way you could produce day and night at the same time at different places on a flat earth. And one of my favorite little memes is there about what happens with a sun on a flat earth and what happens with a sun on a globe earth. On a globe earth, half of the earth is in daylight and half isn't. And on a flat earth, it's either day or it's night. And there's only one way to make night, and that's to have the sun go on the other side. And in that regard, it's interesting to me. I should say that. And one other thing, of course, is the behavior of Polaris. The fact that every time you go some distance south, Polaris goes further down by the same angle. That's another thing that can't happen on a flat Earth, but happens in a perfectly natural way on a globe Earth. And of course, the visibility of more stars. Notice that people in the northern hemisphere, if they really take the behavior of the sky that they see seriously, they have to kind of know even before they see it that there must be some stars that they're never able to see because of the behavior of the stars that they do see, and the clear fact that it's more than half a sphere. It means that there would have to be kind of an opposite pole in the south and more stars down there that you wouldn't see. It's a little less obvious than the fact that you obviously can't have day and night at the same time at different places. So in that regard, a little aside here on modern day, as I've come to call it, robothemism. There's a guy, flat Earth has been dead for 2.5 millennia, and yet it was revived at the end of the 19th century by this guy Samuel Robotham, on the basis of what some people call biblical cosmology. And Robothamism consists of saying, in contrast to ancient cosmologies, that the sun is always above the earth, and that night happens because the sun just gets too far away to light it up, despite also being very close to the earth and never going outside the bounds. And so that little circular disk in the first instance represents most Robothamists' idea of the way the earth is. And this guy Peter Markley is really an interesting guy. I've come to recently enjoy a lot of his YouTubes. He is a young earth creationist. He believes that dinosaurs rode on the ark with Noah. And he is, along with a few of us other fellow young Earth creationists, one of the most vociferous and I think eloquent anti-modern, anti-Robothamism guys. And so there's a video there I've linked to him talking about Robothamism in a debate with a Robothamist, which you might enjoy. But I also like his little Venn diagram there. He points out, so the major categories in this Venn diagram is whether your model explains time zones, whether it's a flat Earth model, and whether it explains the sunset. And his point is that ancient cosmologies are based on flat Earth and explain sunset. The globe model, what ancient cosmologies don't do is explain time zones. For ancient cosmologies, the sun is overhead at noon. When it sets at 6 or whenever it sets, maybe at different times for some reason. That's weird, but it sets and then it rises again. But it sets and rises at the same time for everybody, so it doesn't explain time zones. The globe explains sunset, like ancient cosmologies, and explains time zones. And it's, in fact, it's the time zone problem that ruled out ancient cosmologies. Robothamism has this weird way of explaining time zones without allowing the sun to set. So it explains time zones in the sense that the sun is closer to you at certain points of the day than it is to other people. And then when it's far away from you via some magic, it turns to night. So you get time zones, but it really doesn't explain sunset because the sun literally cannot set in a Robothamist view. So I really like this Venn diagram. It took me a while to appreciate just how cool it is. And I'll just commend that link to anybody's attention who would like. Any comments on this before we go on? Anyway, but the point is that we've now 2,500 years ago thoroughly dispatched the idea that the Earth can be flat, and now we move on from there. Any other comments?
Just very quickly on your last comment there. Again, we need to think back in the terms of old days, and the means they had. Just because a few scientists had that weird idea that we live on a big globe, and they had very clever proofs of it, and they wrote it down on a piece of papyrus, and they sent it to the library in Alexandria. This does not mean that the large amount of the population has gotten rid of that idea. You will see in colloquial writings and people writing their memoirs, etc., a lot of reference to the four corners of the Earth, to the flatness of the Earth, to I'll throw you above the edge of the Earth, etc. Even when you are very important, the writings that have survived are the writings of very important, very educated people. Still, you get that sort of signals in their writing that in their minds the Earth is flat. And so the flat Earth did not really die, but it died scientifically speaking. If you are, the beneficial today of, or the sun, let's say, we are the grandsons and daughters of that method, then we can say, oh, our grandfathers have gotten rid of it. But not for the large amount of the population. Most of them still believed it was flat.
It's interesting to me, Shamash, because I guess I have always kind of certainly labored under the impression that there were a lot of people who weren't educated, of course, until quite recently. And it wouldn't be surprising at all that they retained ideas of flat Earth. I am a little surprised to learn that people of any education could have retained that. That'd be an interesting. If there is a source that talks specifically about the persistence of that view among educated people, I'd really be interested in
I can give you a
seeing it.
very quick one immediately. Yeah, we know that it was the Greek philosophers who really cemented that idea of the globe Earth, whether it was Aristotle or Plato or later on Eratosthenes who really measured it. But at the same time, we know that Alexander the Great was the private student of Aristotle, and we know that he believed in a flat Earth. So he was racing his military to get to India because in his mind this is the edge of the earth, and no one has ever seen the edge of the earth. So
Well, that's a,
that just shows you that education wasn't as we think of it today.
I think that, I mean, it would make for a really interesting book to explore the persistence of the idea among educated people and how that happened. I'd be interested in reading a book like that. So anyway, thanks for that. I will, I certainly don't know better than you, so I will take your word for that, but that's surprising to me. Let's move on to slide 8. So what replaces once we get rid of the idea that the Earth is flat? That's not a big problem, right? I mean, it actually, you say, oh, okay, fine, the Earth isn't flat. Oh, okay, well, it makes sense, right? We can now explain night and day at different places. There's no need to change our views about the celestial sphere, really none at all. You could have had the Ptolemaic system largely with a flat Earth in the center. It wouldn't have changed virtually anything. The only reason the Earth isn't flat in the Ptolemaic system is that Ptolemy knew the Earth wasn't flat. it's a globe in the center there. But you still have everything going around it, just like you do, just like you always had. You have all of the planets, all the wandering things, largely confined to this same path near the ecliptic, going around the Earth. You have to do, you have to somehow explain why Mercury and Venus actually never get very far away from the sun. In the diagram that I've shown here, Mercury is in an impossible place, a place that would put it directly overhead at midnight, which it never is. So in the Ptolemaic system, Mercury and Venus were kind of locked to a line between the Earth and the sun and executed little epicycles around the place of intersection of that line with their orbits, which made them weird. Everything else kind of basically just went around the Earth on its own, except that kind of in little epicycles and epicycles on epicycles. The Ptolemaic system is kind of simple in this diagram, but it turned out that to get accurate predictions, you had to actually put all the planets on little circles centered on the place on their orbit, on some place on their orbit, and then little circles centered on a little place on that circle that's centered on a place around the orbit, cycles, epicycles on epicycles, and all of that was really just put together, and the numbers all worked out so that they could make accurate predictions about where everything was going to be on any given night for no reason whatsoever, other than maybe to aid astrologers in figuring out what was going to happen at some point because of where the planet, what constellation the planet would be in at that point, etc. So it does allow now day and night at the same time at different places. It explains the globe, as long as you have the globe geocentrism, explains the behavior of Polaris, visibility of stars as one travels south. Stuff still falls for the same reason. It's just trying to get to the center of the universe. Stuff in the heavens still obeys its own kind of unknown supernatural rules. It's not a very big change, right? Just realizing that the Earth was flat was obvious and really didn't cause any particular upheaval. The church is able to embrace Ptolemaic, the model, pretty easily. Didn't cause no upheavals. Any comments on that before we go on to slide 9? We're getting pretty close to the end here, amazingly enough.
Just, I don't know if you want to talk about that, but the retrograde motion as well, it had a fix.
Right. That's right. So the Ptolemaic motion, the first epicycles, the epicycles themselves were a way to explain the fact that the planets seem to move a little slower than the sun does, the outer planets at least. Well, they move at different rates, but they sometimes move forward in the celestial sphere and sometimes backward against the celestial sphere for a short time before continuing in their forward direction, and the epicycles. I won't go into that now, but the nice thing about the Ptolemaic system and epicycles was you had some way of kind of explaining that. But once again, you could have done that with a flat Earth. The difference between the Ptolemaic globe geocentrist model and the previous flat Earth model is minimal to non-existence. It's just a recognition that the Earth is a globe. Nothing else really changes.
Yeah, that the story is that the explanation was the planets go in retrograde because they're the kids like of the gods in heaven, they have like little kids and they start playing with these planets. So like it never was anything surprising for those. Of course, it was surprising, but it never pushed them to get away from metaphysical thinking. All it is, okay, let's invent one more story.
Right, it's magical to begin with, so it's not you don't
Exactly.
have any explanation for any of it, so it's just the way it is. And the one thing you can say about it is it sure isn't the way it is on Earth. That's the one thing you can say kind of for sure. But so we lived with the Ptolemaic model for a millennia, more than a millennium, and then at some point it was realized that you could actually get the retrograde motion if you just made one seemingly small change, right? So Copernicus made a seemingly small change. You just say, hey, what if the sun is the center of this big bright thing? What if it's the center of the solar system, and the Earth and all the other lights in the sky rotate around it, except for the moon, which rotates around us. And later, the version that I have there actually shows the Galilean moons of Jupiter. Copernicus didn't know about the moons of Jupiter. He didn't really know that Jupiter he didn't know that the other planets were like the Earth. He probably suspected that, but there was that wasn't a motivation for the model at all. It was just a nice way to explain retrograde motion. But it came with, in contrast to getting rid of the flat Earth, this came with the all but unacceptable expense of any reason at all for stuff to fall to the Earth. As soon as you put the sun at the center of the universe, you have an enormous problem at your hands. Why does stuff fall to the ground? It becomes just an enormous problem. And so it's really...
Why don't they fall to the ground is the real problem, because you assumed that everything falls to the ground, and now you're saying that there's things out there that just rotate freely. Why would they not fall?
Okay, so I guess I think what you mean when you say why don't they fall to the ground, you mean the sun is now the ground.
Either that, or why does not the sun fall down to us? Like, okay, we're not the center, so now we're rotating
really
around it.
Point.
So you know what I mean? Yeah, it loses the perspective at that point. The whole thing of up and down just loses meaning before you have that perception.
Yeah. No, that's really the point. Is that the moment you take the Earth out of the center of the universe, let alone have it moving around the sun, now you've got a really thorny problem on your hands. I mean, that's what Copernicus was. People didn't have any trouble accepting the globe. Educated people could be told in a few words, it's night somewhere, we're in stay here. Oh, okay, never mind, I get it, right? But taking the Earth out of the center of the universe it was an incredible step. Because all of a sudden you have to explain why when you drop a rock, it falls to the ground. Why would it do that? There's no reason for it to do that. And it's a big problem. And yet people kind of accepted it because it really did go a long way toward, it got rid of the first layer of epicycles from the Ptolemaic model and completely explained the idea of retrograde motion without needing to appeal to epicycles at all, even though the Copernican model did ultimately require epicycles to match observations. Philosophically, it was a huge step because it did at least explain foundationally why you would have retrograde motion without the need for epicycles.
John.
Yeah.
I guess I lost track of where the caveman got left behind. Because there were other phenomena that don't seem to fall, like clouds, wind, lightning. We haven't tried to explain those phenomena, but I think that's how you can see how mythologies and things. There's a whole lot of other unexplained phenomenon than just the movement of the stuff way
Yeah.
up beyond the sky.
No, I
'Cause
agree.
the
Those are really good points.
atmosphere. Remember the earth, wind, fire, water
Right.
elements.
Right. And I think you're exactly right, Dave. And I don't disagree with that at all. I will say I'll only defend myself by saying I just don't really want to talk about that angle. But that is another huge angle, right? There's all sorts of mythology. It's hard to just, I did mention the sky being blue. Why is the sky blue in the day, right? And there's all sorts of things associated with the atmosphere, atmospheric phenomena, lightning, etc., that I'm completely leaving alone here. Yeah, good point.
I just mean that it doesn't make gravity a slam dunk.
No, that's right. No, and we're not even there yet, right? All I'm saying is that at least that now you can't even explain why a dropped rock falls to the ground. And that was perfectly obvious when the Earth was the center of the universe. Now you have no reason for a dropped rock to fall to the ground. And yet people kind of persevered with this model because it did do a really nice job of explaining some stuff, right? Copernicus was resisted enormously because it did explain some kind of big things pretty simply, but it really left you completely at sea with regard to why dropped rocks fall. And Kepler, Kepler just is essentially just a refinement of Copernicus. It's worth mentioning because Kepler was the first to kind of give three mathematical laws that applied to all of the planets. Everything, all of the planets in the sky can be understood with three simple, purely mathematical laws. That was a revolution of its own to understand that, much more so than Copernicus, which really wasn't ultimately, the brilliance of Copernicus was not really mathematical. It was just kind of phenomenological, right? It's just a different way of things doing it. But Kepler had its own problems, far smaller than Copernicus, because it got rid of once again, kind of just the assumption that whatever motion there was going to be in the heavens had to be at its base circular because circles are perfect. And, the shape of the sun is a circle, the shape of the moon is a circle. Things seem to move in circles around the Polaris. There's all sorts of reasons to think that circles are just perfection. No real reason to pursue that any further because whatever it is that made the heavens and the earth would certainly opt for perfection. So Kepler had problems. The idea that there are ellipses, that things don't move at constant speeds, that a lot of things that were puzzling, but not nearly the revolution that the Copernican idea of taking the earth out of the center of the universe. Still, you have stuff in the heavens kind of obeying its own, now at least partially known rules, not really known why. Why would the square of the period of a planet be proportional to the cube of its average distance from the sun? That's a pretty weird thing, but it does appear to be the case, and that's about all you can say. So I've got kind of a mathematical diagram of Kepler's laws there, just for you to kind of put that on. But we have now, at least started on our way of taking the Earth out of the center of the universe. And there is, I just want to really leave you on slide 9 with an understanding that there is now a huge problem. Why does stuff fall to the ground? Okay. Yeah, Andy?
Hey, John, I apologize. I am driving and I am not flying the slide, so I might have missed something. But isn't there like a middle step? So Ptolemy had the Earth in the middle, and everything went around it in concentric circles, including the sun, right? And then I thought there was
You're
a
going to
step.
go to Tycho Brahe, probably. Huh?
Maybe is that so? Is that the step where it's like, hey, the Earth is still in the middle?
Yeah.
but the sun goes around the Earth, and everything else goes around the sun,
Right.
which like mathematically is equivalent, but still keeps the Earth in the center. So
That's right.
how long did that idea persist before they were like, all right, you're basically saying that the sun is in the middle?
I think it's fair to say that that idea didn't persist at all, that most people at the time didn't even know about it. There would have been astronomers who would have known about Brahe's work. Brahe was not really so much an astronomer, although he had wealth and he put together a great observatory, took great observations. Um, and as you say, I've left out any mention of Tycho Brahe only because it doesn't really matter for the story I'm telling. But since you brought it up, I'll just mention that, yeah, the Brahe system was basically exactly what is, but has everything rotating around the Earth. So the moon rotates around the Earth, the sun rotates around the Earth, all of the planets rotate around the sun. The sun carries them around the Earth with it. The distance and direction to every planet is exactly what we observe it to be. There's no kinematic, as some people like to say, there's no kinematic way of distinguishing between the Brahe system and the system we know. It gets all the distances right, all of the angles right. His system didn't, because he didn't really know that the orbits had to be ellipses around the sun, etc. But a Brahe type of system is really just taking the actual universe and viewing it from the Earth as if the Earth is not moving. And you can always do that, but then you're left with the problem of trying to explain why the entire universe wobbles back and forth once a year rather than just having the Earth going around the sun once a year. Yeah, anyway, that's so that definitely was an intermediate thing there. It just doesn't fit neatly into the particular story I'm telling. Okay, should we move on to slide 10? So slide 10 then is really to set up this whole stuff attracting stuff. Why this is such a huge thing. So here comes the first actual physical theory of the universe. And we've only had one since. So there have really been two, I would say, physical theories of the universe, Newtonian and the general relativistic theory. Newton came in, did an amazing thing. First of all, he basically just said everything is stuff. Stuff up there is stuff down here is stuff. It's all the same stuff. It all obeys the same laws. There's stuff everywhere does what it does because of forces. And the Newton's second law tells you what it will do if you exert forces. All you have to do is calculate forces on things, and that will tell you what it does. So everything is stuff. Stuff everywhere does what it does for the same reason, forces. Here's exactly what it will do if you find the forces on it. And then finally, and probably most importantly, stuff attracts stuff. Crazy idea, maybe motivated, maybe only having a predecessor in the magnetic effect that we've talked about. You can have magnetic attraction. You can also have magnetic repulsion. But Newton said, no, stuff, in general, on large scales, stuff just attracts stuff. Stuff doesn't repel stuff. Stuff attracts stuff. And then he has his law of gravitation, simple law. The force that one object exerts on another to attract it is the product of the masses divided by the square of their separation, and that's it. And that's it. Those two laws fundamentally explain everything that happens in the entire universe. And the most important element of it is this novel idea that stuff attracts stuff. Novel and crazy, right? A crazy idea that stuff attracts stuff. By the way, that's not really a thing in the second theory of the universe, the one we have now. It's not true that stuff attracts stuff. It turns out to be a result of the way the universe works, that stuff looks like it attracts other stuff. And that's fine. We can still say stuff attracts stuff. But that was a really novel idea. And it's that word that I'm not going to say. I don't think I've said it yet. Other people can say it, but I'm not going to say it. Stuff attracts stuff. really come. So let's just take one last slide and talk about the implications of stuff attracting stuff. Well, if that's true, then kind of as we said at the beginning, stuff's going to clump up. Big stuff is going to get spherical because materials have limited strength. And if you get big enough stuff, it's going to really, you're going to have a lot of stuff attracting other stuff. It's going to attract other stuff so strongly that it's going to want to get to be in the most compact form it can, and that's a sphere. So big stuff is going to be spherical stuff. Fluids are going to stick to the outside of big solids. Oceans and atmospheres stick because stuff attracts stuff. That's all you need to know. And big enough stuff has really high pressure at the center. And ultimately, when we learn other things, other laws that Newton didn't know about, nuclear laws, which have no place in this story, we can start to understand how stars work and how all that kind of thing happens. But for our purposes here, it's just enough to know that stuff attracting stuff makes things spherical. And then other implications from the idea that forces change motion is that when you put that together with stuff attracting stuff, you get orbits. In fact, you get exactly Kepler's laws. One of the most remarkable things about Newton's two laws is that if you apply them to one thing attracting another thing, but having some kind of sideways velocity, is that they'll always fall toward each other by the attraction, and that falling will lead to them moving around each other perpetually in orbits that obey exactly the laws that Kepler determined just from looking at observations and saying, oh, this works. His first, his second, his third law, he simply derived purely empirically from no foundation, and Newton's law predicts all three laws precisely. They're mathematical entailments of Newton's laws. So that's kind of a cool thing too. Anyway, that's the story for today. We can talk about other things or talk about more, hopefully talk about this a little more, ideas from this a little more, and then we can go off into other things for a little while, but maybe not more than half an hour or hour at the most.
Are we allowed to add our professional
Isn't
observations?
Yeah,
stuff
absolutely. Anything
like-
you'd like to say.
Like
Let
in
me-
oil,
I'll
like
read
in
the
oil
chat.
and gas, as we drill deeper and deeper, the pressures do indeed go very high, and temperatures as well.
Right.
It's not doesn't fit into this, but I'm just saying that we have a lot of empiricism on top of where you're going.
So it's an interesting thing, of course, that if you think about stuff attracting stuff and you have a lot of stuff like 2 times 10 to the 30th kilograms of hydrogen getting close enough together to really, compact itself into a dense fluid of hydrogen at the center of that thing, you're going to have really high pressures. At some level, some kind of high temperatures. As you compress something, it tends to heat up too. But not as hot as the sun gets. There's something else going on at the center of the sun that we didn't really know about until about 100 years ago. That's another kind of just interesting story, of course, is that the universe couldn't have been more than 10 million or maybe 100 million years old, or at least the solar system couldn't have been 100 years ago, because there was nothing to keep the sun alive for that long. And yet the mounting geological evidence was that the Earth was billions of years old. You couldn't explain that, since everybody by that time was pretty clear that the Earth was formed after the sun. If the sun couldn't live for even 100 million years, how do you explain that? So the discovery of nuclear energy was kind of an important step in the process of another story that I haven't told today.
Stuff attracting other stuff. I mean, ultimately, it's a bit of a circular reference, isn't it? Because the definition of stuff is that which attracts other stuff.
Yeah, that's right. I kind of chose the word stuff in a way because I didn't want to get bogged down. There's a question of whether the vacuum is stuff, right? This seething quantum um, vacuum is kind of a funny thing. Is that stuff? There's a lot of modern questions. We still don't know all the answers to those questions. But fortunately, I only had to get us to about 1750. Andy?
Yeah. So when people first started thinking of forces, I think Newton wrote a little bit about being bothered by, I guess, what we call now action at a distance. But was how do people think about it? Because part of me always feels like, well, if you're going to start talking about a force, okay, we're really not just like, this must be an emergent um, phenomena of some sort. There must, on some smaller scale, there must be another explanation of what's really going on, like with particles or something, with more stuff, like another version of stuff. Um, and I sort of feel like it's only been recently that people have started to say things like, no, wave functions are just those are the things. Those are the things that exist. Like that's the fundamental thing, actually. So how did people talk about that back then?
It's
Think about
a
it.
it's a good question. I think the idea of force itself is an interesting. I mean, the history of ideas about force. Once again, if you kind of put yourself in a caveman's mind, it's pretty simple. When you touch stuff, you can manipulate it, right? I don't know that you have to really. I don't know that you have to think really very detailed manner about forces when the only kind of force you ever really deal with in daily life is a contact force. And of course, we now kind of the modern view of things is that is not, first of all, we've kind of gone away from the idea of forces. We usually talk about interactions. A force in the Newtonian sense is half of an interaction. The other half is the reaction that Newton talks about in his third law. But it's really the interaction. And when you focus on the interaction, you realize that Newton's third law is really just a way of looking at probably the more fundamental law, which is conservation of momentum. That when things interact, they interact in such a way that the momentum of the system is conserved. And so, yeah, elements of the system will be forced to do something else. But the important thing is that the system maintains a constant momentum. And so you have interactions and then you have systems that have constant momentum. But the really important thing is not Newton's second law, or Newton's third law in a sense, but conservation of momentum.
Can I add a few things just to answer the question, John? Hero, you're asking a very curious question, and I'm not sure if people in the scientific community appreciate this discussion enough. And probably if I can plug the Philosophy Wednesdays here a tiny bit, there's this movement in the early 20th century that the story of the discovery doesn't matter, but we'll get to that. We'll get to that on Wednesday. So people neglect these things. But to answer your question, so how did people start thinking about forces? Well, you had first of all Galileo, and Galileo started doing all these experiments with falling objects. And the genius move he made was he had an inclined plane, like a ramp, like a wooden ramp, and he would roll down objects, because in his mind, I need to observe the falling object slower, because it's just too fast for me to see as it falls in free fall. So I just need to slow down that fall. So he just did these experiments with falling objects along a ramp. And the thing he discovered is the inverse square law with acceleration. So things are accelerating based on that thing. And that establishes a pattern. So you have that. Of course, he did other experiments that have to do with heavy objects and light objects falling down. So he dropped a pebble and a big cannonball from the Tower of Pisa, and they arrived quasi at the same time at the base. So people kind of starting to believe that there is a pattern with falling objects. It's not random, like Aristotle believed, for example. It goes flat, like horizontal, and then it falls down 90 degrees. No, there is a certain pattern here that is emerging. The other major thing I would say for Newton was that at his time, we had around 250 to 300 years of navigation. And when I say navigation, I'm not talking about the kind of navigation that, oh, there's a vessel and it just travels like 50 kilometers away from the shore. Not 50 kilometers, I mean 5 kilometers away from the shore. No, like we observe the shore and we just travel around it. They had magnets and they had maps and they had very complicated tools. And of course, they had compasses. And so the idea that an object is affecting another object by distance wasn't that weird anymore. People on ships knew that you shouldn't be putting metal next to that compass because you will get lost at sea. So the objects will interact in a weird way on distance. That's number one. Number two, there must be a pattern in these falling objects because we have the observations of Galileo. And then if you put the two things together with Newton's brilliance in mathematics, he posited the existence of this thing that causes things to fall down. And it's the same thing because there's a pattern. And then if you want to call it force or call it whatever you want at that point.
Yeah, thanks, Shamash. I was just taking the opportunity to read some of the comments. I want to apologize to Assam for insulting Neanderthals. That wasn't my intention. I guess he must have more Neanderthal in him than I do. I think I'm about 60. I can never remember whether, I think 23andMe said I have more Neanderthal in me than most. But I think I'm starting to understand that may be a compliment, because I think Neanderthals were maybe smarter. They just weren't very good about surviving. They had that big brain, right?
Neanderthal became a compliment as soon as Europeans realized that that all the Neanderthal latent DNA is in Europeans. So they made it a compliment.
Yeah.
So I'm sorry that Wisdom felt bad for a minute. Wisdom, we'll do what we can to make you feel good again. Somebody stroke Wisdom.
I also see that
Also
there's
Wisdom.
quite a theological discussion going on in there. It's funny to me. I don't really. I link to this guy who is a young Earth creationist who believes that dinosaurs rode on the ark with Noah, and I've run into people like that before, and it's made me kind of appreciate a new thing. I mean, I think there is this strain of very fundamentalist religious types who I think distinguish themselves by being slavishly devoted to evidence. And especially when it comes to evidence for things that we can see now. If you want to talk about, what are the laws of physics? What are the evidence for it? What do we see in the ground? There is nothing that they will just knee-jerk deny if it's something that we see now. But the bridge too far for them is drawing any implications about things that happened in the past from stuff that we see now. And I think it's an interesting, I'm not going to call it, I don't think it's a particularly laudable approach. I think it's interesting to me that people who are just slavishly devoted to the scientific method when it comes to what is in the present can have such a different attitude towards implications that we can draw about the past from evidence. I get it. I think it's not absurd, but it's just interesting to me that there is that breed, and that breed of religious person. It's interesting to me that they are particularly offended by robothamism, because it is a movement from within their own ranks that they find to be offensive because of the fact that it makes them all look like morons.
Right, they're like, hey, we're trying to be credible here.
Right. No, it's interesting, and so I've formed kind of a particular bond with young Earth creationists of that ilk. Go ahead, Benjamin.
I'm fascinated by the endearing fact that you still think that there is a one and only scientific method. charming.
Well, so I don't remember who said it, but I do take the attitude that the scientific method is doing your damnedest with your brains to figure out what's going on. I think that's the scientific method.
Yeah, sounds a bit. It sounds a bit. What do we call inclusive?
Yeah, well, it was intended to be. That's why I was a little surprised when you said that I don't think there are, what did you say? That I don't think there are.
Oh, you said that there was uh, the scientific method, as if there was one and only one
Well,
scientific
there is
method. I
one and
just thought
only
that
one.
was
It's doing the
an
damnedest with
endearing
your
and
brain to
charming.
figure out what's going on.
Oh yeah, sure it is.
Yeah, I don't know. Shamash and I should, yeah, we should all have an argument about that sometime. And I can't remember who said that. I should remember it more because I refer to it all the time and I never get it right. And then I also don't get the attribution right. Maybe I'll look it up. If somebody else has anything to
But I
say.
think today was really an example of how Sapiens would have written this story, right? Which is a lot of people doing their damnedest to describe what they think is going on, and then a lot of other people being attracted or repelled by those explanations, and then people attracting themselves to different stories to explain what they see, and that's why we end up with a couple constellations of stories about stuff in the universe. We have like religious stories, we have a-religious stories, we have sort of supernatural stories, and those supernatural stories vary in a variety of ways. But they're clustered because people just gravitate towards stories. But if science is just a contest to see who can make the best story and get the most people to subscribe to it, then it's just a popularity contest, right?
Well, I would say that the one thing that distinguishes science ultimately is that it is if you're doing science, then you have to accept experimental evidence. Nature always gets the last word. If there's one thing I absolutely demand, it's that nature gets the last word. If nature does something that a theory that we have denies, and of course showing that's difficult sometimes, but it is certainly the case that if the consensus of experts in the field is that nature does this, doesn't do that, whatever, and if it in any way, if whatever it does or doesn't do conflicts with the predictions of your model, then your model is wrong, period.
Yeah, but that can get dicey because the mechanism of your experience can kind of lose itself in the weeds. Like
Right, I agree, and that's where
I'm
the role of consensus comes in. And consensus is, it's not 100%, but
but if there's a
it's a big
role for
deal.
consensus, or if consensus is that thing which distinguishes between good theories from less good theories, you're right back to population contest. You've got nothing burger. Look, this is from page 5 of the Delft experiment, right? Shifting the window back in time, the relative fraction of heralding events caused by clicks from the excitation laser reflection increases, thereby reducing the observed Bell violation. That sentence just means that, well, we have some noise in our system over here and we discount that noise. And when we discount that noise, then we get the quantum result. And if we don't discount the noise, we get the classical result. So the difference in outcomes of this experiment boils down to the relative fraction of clicks caused by laser reflections. But the problem is that the clicks look the same. They're not green clicks and red clicks.
So
There's
Benjamin,
this
I'm only going to stop you because I'm not going to respond to anything that you're saying here, and I don't think anybody else
No, I
even knows
know,
what you're
right. But
saying
but the
here.
point is you can do the empirical experiment, but the empirical experiment has these kinds of ambiguities. Right, and I don't think you have a theory for dealing with those ambiguities. You just say, well, you have to accept the empirical result.
Yeah, I'll just stick by my original statement, which is that in the end, the great thing about science is that nature wins. If you have a theory that makes wrong predictions, nature will tell you that.
Wisdom has a good quote in the chat, and as always, he can listen much better than he can participate. So I'm going to read it. Wisdom says, "There isn't a scientific method. If you think that means there is only one method, or if you think there is a method or methods that distinguish science from unscientific methods."
Well, I think I agree with that, as long as Wissam's also willing to agree with me that when that science decides on theories based on what nature says, not on how beautiful. I mean, you may be attracted to a theory, but it doesn't matter how beautiful a theory is. Newton's theory is I would be willing to wager a bet the most beautiful theory in some sense, if you count simplicity as important, that we will ever have of the universe, and for that reason we'll always use it. And we know it's wrong, fundamentally wrong, even though it gives really good predictions. Fundamentally, we know it's wrong, and that's not up for debate. Unless you debate what the meaning of wrong means, which I think Andy might be willing to do, but I think he knows what I mean when I say that too. It will always be used because it's beautiful. Its simplicity is absolutely stunning and will never be outdone, and it's wrong.
So Andy, very, very late to the party, has commented. He says, "It is dawning on me that the reason Benjamin dislikes popularity context so much is simply that he is bad at them." And I have to congratulate Andy for being dead
Pithy.
last to the top of that mountain.
It's pithy. So we have John. We have John on the stage now too. Go ahead, John.
Hi, yeah, I'm listening to your conversations. To me, science is just a tool for us to understand the real world, if there's a real world. And every time we use this method to know the world, get to see and actually see we have some subjective views on what we are doing. And we have a concept. See, for example, every time we do science, we already have some kind of idea or concept of see, for example, I'm working on a project. Actually, I have a hypothesis already in my mind. If what we observe fit our concept, then we think our concept is right, our theory is right. But sometimes it might bring in those prejudice, because we might think this is right, but actually it might not be. So when you talk about Newton's law is so simple, and yes, it is so simple, but the problem is that it might not really exactly fit the real world, because the real world
We know
is
it doesn't. Yeah, I mean, we know
yeah,
for sure that it doesn't.
exactly. So we always see we have this abstract thinking. See, like a line is a straight line. It's see, like a point is zero. See, like just is minimal. But in reality, there's no straight line. There's no see like a infinitively small point. So when you use this, see, like you can see, for example, you draw a map of a city. You can see like a scale this. You can use different lines to see. Okay, so if you use 1 to a million or 1 to uh, 1,000 or so, you will find that this reality is different. So, and you have to really see make your model see like a more and more fit the reality instead of make the reality fit your model.
Yeah, no,
So
once again, I mean, I just want to really emphasize when we find flaws in our models, sometimes they can be patched, sometimes they have to be abandoned, but one way or another, it needs to be fixed, right? If nature wins, there's no trying to beat nature into the shape that fits our model. That's if you're doing that, you're not doing science because
yeah,
scientists don't do that.
I agree with that.
Yeah.
Yeah, so that's why I say when we become more and more close to the reality, actually our theory has to be more and more complicated.
See, I don't know that that should necessarily follow. It seems
Yeah,
kind of in a
it might
sense
not
that
be.
it does. And
Mhm.
it's kind of beautiful in a way. It's its own beauty, right? Quantum mechanics and general relativity are extraordinarily complicated. Mathematically, quantum mechanics in particular. I have a favorite cartoon that maps the number of years to understand a theory on the horizontal axis and the degree of innate interest in on the vertical axis. And quantum mechanics is way up there at the top in terms of innate interest and the number of years to understand it mathematically. And the punchline is that this is why there's so many weird ideas about quantum mechanics. Everybody's interested in it, nobody understands it. And so that's really the tension. But let me, John, I appreciate your comments. I realized that I skipped over Dave Linst, who's on stage too, and I wanted to give Dave a chance to say whatever he has to say. Dave, are you there? Yeah.
Yes, yes. So basically, I think humility is the foundation of good scientific method. Once we lose this perspective of this humility, then we we assume whatever we are doing right now is sufficient until we are further humbled again by problem we couldn't solve, and the death is not hundred, not thousand, but double-digit millions, and we try to bury those truths, right? I agree. The nature is the source of inspiration that humble how little we know, right? And how limited our scientific method, and how inadequate our sensor to be able to collect data that help us to justify the continuation of the existing scientific method. And also sometimes because of the consensus among the scientific community, they said this is what I have. If you don't let us do this, I can't publish. And for that pressure, the scientific community consents into compromise, and that limit the breakthrough in science that might potentially save double-digit millions of life globally. That's the problem.
Yeah, no, I agree. I mean, I think what you're pointing to is the fact is just human foibles, right? We do get attached to our favorite theory, especially if we've had a hand in putting it together. I have never been in that situation. And especially as we get older, right? This is why Nobel Prizes are typically awarded to people for work they did in their 20s or 30s, because they're not as kind of frozen. It's exercises like the one we went through today. I love these kinds of exercises. Not to say that the one we did today is particularly mind bending, but I think too few people take the time to really ask, why they know what they know. The whole epistemology of we are indoctrinated, and the fact that we're indoctrinated into stuff that is for the most part true. And there's a lot of things that are just true, like the fact that the Earth is a globe. That's just a directly observed fact. That's not a conclusion of a scientific theory. The fact that is true doesn't change the fact that most people think it's true because somebody told them it's true. They've never done anything to prove to themselves that it is. They've probably made observations that they could use to prove that, but never thought to do it. Never made them precisely enough. Anybody can look at the constant size of the sun and prove that the Earth isn't flat just from that. But most people don't really understand how to do that. So, yeah. Anyway, yeah. Thanks for that contribution. Anybody else? Anybody down there care to come up? I was saying, I see we did have kind of a theological thing going on in the chat. I'm going to have to. It's too much for me to bring myself up to speed on right now. Not that I would care to, probably, except I do. I will take a look and see what was going on there later. Any other comments? We'll maybe start winding down. That usually stimulates Benjamin to say something.
Are you just trolling me?
Well, not really. I mean, it does seem like that's kind of the case.
Well, we were going to do a second room about
Yeah,
the aircraft accident.
helicopters and so
So
on. I think I won't start that room, but maybe Andy or you or Ben Tristram will do that. Ben's probably off doing family time right now, but he's usually available in an hour or so. He might be available now, I don't know. But I would suggest maybe getting in touch with him and thinking about a room like that. This is
He's just going to tell us that we shouldn't be talking about it.
Sorry?
He's just going to tell us that we shouldn't be talking about it.
That's true. He already said that, didn't he?
He wants to wait 4 years.
He's a buzzkill. He wants to be careful and professional and judicious.
Yeah. Hey, where are you now, Andy?
I am in Bakersfield.
Oh, sorry.
Hey, speaking of the devil.
The fun thing though is I read about this. There's a famous liquor store that I just went to and bought two. They're famous because they have all these like pre-mixed drinks. You know, they got the little bottles of liquor and so they have all these cocktails that are kind of like ready to go.
Bullet old fashions.
Yeah. So I know it's only 11, but I stopped and grabbed two of them for later.
You know, when you that immediately puts me in mind. My wife and I went to Costco the other day because they used to have those really nice Bullet old fashioned and Manhattan pre-mixed. Just pour it over a glass of ice and enjoy things. And then they stopped having them a few months ago. But now they've come out. There's a Kirkland bottle of old fashioned. It's a liter of old fashioned for $16. We haven't opened ours yet.
That's too cheap for your own good.
I don't know. I mean, Kirkland stuff is usually pretty good, so I'm looking. We haven't opened it yet, but I'm looking forward to it. Hey Ben, you're back.
Maybe I will stop by.
Yeah. Oh, the only unfortunate thing is we forgot to bring it out to the beach, so we don't have it here. You'll have to stop by Costco and get one on your way, or we can just make you a real one. Welcome back, Ben. We're
sorry, long way to the mute button. Yes, thank you. I just had dinner. I just didn't want to accidentally unmute and release any medical noises, chewing noises into the.
Are you ready to discuss the accident?
Well, yes, but my typical thing is let's wait 6 months to 3 years to find out what actually happened, and I'm quite serious about that because often, I mean, I think they found the CVR on the voice recorder now, right? So and the flight data recorder, voice and data, but they've got to process all that and work out what it means, and that might not tell them anything, and then they have to find other bits. And I mean, literally can take, I don't know how long an NTSB report, the longest they've taken, 5-6 years maybe. It could be that long.
Andy predicted that's what you would say.
There are some facts, Ben,
sure
because your dogmatic belief to wait so long. I think you might not know just how much telemetry we already have and exactly
I know nothing about it.
Some of the stuff that we already know. That's what I think they were going to start with, and then you could duck out in the speculation.
I mean, you can often get the cause pretty quick, but the recommendations for what you do about it is what takes a lot longer. Which is really what I'm.
5 years.
What is Clubhouse going to do about that? Publish
they can't wait 5 years to update their procedures in that area, can they?
Well, Um, you know how it works, Benjamin. It's a big topic for you, right? They try and get a preliminary report out about the cause as quickly as possible for all the people who want to know and the families and all the rest of it. And they also, if they can find anything, they basically release guidance about how to prevent a similar thing as quickly as possible. And if there's an uncertainty about what caused it, then often they have to ground the whole fleet. That's the first time pressure. Is like, if we can't find out why this type of aircraft or why this happened, we need to ground the whole fleet. So I mean, there's a massive
Well, in
time
this
pressure, but
case,
even with that massive
that
time
would
pressure, it can
mean
take years.
closing the Washington Dulles Airport. No, not Dulles.
Maybe
It's
just
the
that
Reagan.
that runway. I think that runway 1 is possibly going to not be used anymore.
It'd be easier to shut off that helicopter route 4. You could just stop doing that right now. You could just stop allowing helicopters to fly that route.
It seems
In fact,
like such an obvious thing,
I have a
right?
feeling they've probably done that already.
Yeah,
Well,
but
I don't
why
even.
would
I've
you?
not
That's
even.
very heavily
What?
trafficked by helicopters. Marine One, their dignitaries are flying helicopters apparently all the time there. So
But make
I,
them fly. Make them fly over the airport at some altitude, right?
they were
But
200, they were 150 feet too high.
why not?
can
But
some can
why wouldn't you just have them fly over the airport
Yeah, that's what
itself?
happens at H1 at Heathrow. I mean, I could probably be more helpful than I'm being here. I'm being a bit dogmatic, as you said. Let me try and be more helpful. Firstly, I know nothing about it, the actual accident, but I have flown heli routes through
Wait,
London around Heathrow,
the
and I have.
helpful thing you could do, Ben, is to open up a room so we can start the discussion. That's
Yeah,
what
and
you
Oh,
need to
I
do.
think
go
maybe
on then.
I will execute my prerogative here to say I don't really want to end this room this way anyway. So
Yeah,
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 open
I'll do
another
that. I'll
room.
open another room
Yeah,
now.
yeah, yeah.
Maybe someone can follow me and grab the link, put it here, and anybody wants to talk about it, we'll
We
try and do
should
it
end
properly.
this room the way we end all of your rooms, John, which is to say that there's just no evidence for quantum entanglement.
Well, there you go. Okay. So we'll just let that be the last word. How about that, Benjamin? That's how
I mean, it
tolerant I
usually
am.
is, right?
Yeah.
It usually is.
Okay. Well, thanks everybody. Thanks for coming, and we will see you next week. I'm now officially giving you the goodbye look.